So I thought I'd better go through some past papers. For Year 11, this is the higher tier for the sample assessment materials. This is the first one they released. This was not an exam, but these are the type of questions. So here's your formula sheet that I'm going to just stick down by there. I'm going to try and get through this pretty quickly. You've got lots of information here on stopping distance, braking distance, and thinking distance. You can see I've done a little bit of adding up there because it was required for one of these questions here. So I'll just put that there because we may need that. So we're going to go on now to have a look at these statements. Speed limit of 30 miles per hour indicates that it's always safe to travel. Well, it's not, because things like braking and thinking distance affect it. Cars always have a braking distance. Again, things can affect it. Now here, travelling twice as fast always doubles. Well, the speed is, you can't put braking distance or thinking distance on the factor like speed, because if it doubles or if it halves, then there's always going to be this relationship. So yes, it does always double, and I've done the workings out there. If you was to look at this sheet, at 20 miles per hour, it would be, the thinking distance would be 6, and then at 40 is 12, so it doubles. And then I've tried it at 30 and 60 there. So just in case you're wondering where I got it from, I've got all this from this chart. Typical minimum overall stopping distance for 50 miles per hour is 53, and I've done that there. I've just added braking distance and thinking distance. So that's going to equal your stopping distance. Thinking distance is increased by tiredness, alcohol, age, distractions, etc., because these are factors that may... so these are reasons why stopping distances may differ. And I've said braking distances are increased when you've got worn brake pads, worn tyres, heavy mass, poor weather conditions, I should have put there. Describe the relationship between speed and braking distance. So again, I've gone to this chart on this page, and when it was 20, it was 6. When it was 40, it was 24. When it was 30, it was this. And I've concluded that it was a factor of 4. You need to times 6 by 4 to get 24. You need to times 13.5 by 4 to get 54. So as speed doubles, the braking distance is increasing. That's going to give you 1 mark. By a factor of 4, we'll give you the other mark there. And then use these patterns to calculate the overall stopping distance for 80 miles per hour. So the braking distance at 40 miles per hour was 24. It's there. Times 4, braking distance, and that's going to give you 96 meters. And then your thinking distance at 40 miles per hour, because remember I need to double it to 80, was 12. So 12 times 2, because it doubles, it's going to give me 24. When I add these two together, it gives me 120 meters. So let's put those there. Text suggests that airbags reduce the harm to passengers. Yes, they do, because airbags increase the time taken to stop, and they also increase the distance the passenger travels before coming to a stop, therefore reducing the harm. Name another safety feature: crumple zones, side impact bars, seat belts, and then things there to stop people down: speed bumps, speed cameras, speed limits. So I'm racing through this paper because I want to try and just go through it, and you can pause this at your own in your own time. Describe a method each group used to collect data for for gathering information on half-life. So dice are rolled, and all those with a 1 or a 2 or a particular number facing up is removed. Then you count the number left and you record it, and then you re-roll and you do it all again. There's some data they've got, and I need to plot that on a graph, and I've plotted it. So it was a nice easy scale. So they always give you your labels. They'll always tell you which one to stick with. So number of dice remaining, number of rolls. This just goes up to 8. Needed to get to this to 400, and the best way to do that using half my page was to go up in 50s. So each box is now worth 5. Each small box, and then I've plotted that. I've got a little bit of anomalous results. What does this graph really show? It's showing you the half-life. So that's the answer there. So I don't think I need this again. I need to keep the graph out. Use the graph to estimate this quantity. So I've done that by, I drew the line. So I halved it from 400 to 200. I've drawn my line down, and it was about 3.7, 3.8. Bearing in mind, you can have 3.7 rolls, okay, in this case. So you get a mark for the line, you get a mark for the answer. Explain how results would be different using a 12-sided dice. Well, it's going to be a longer half-life because the probability of decay is lower. Okay, this question on stars. It really wants you to give the life cycle of a star and talk about balance, talk about forces and the reactions, really. So I've said on a main sequence which has started, I might not get a mark for this, but I've kind of started as a main sequence. Obviously before this is a protostar. Oh, by the way, this is going to be a big star because it's 22.5 times the size of our stars. This is all information I've picked up from the text. So your main sequence star is going to be fusing hydrogen. That's its main source of fuel. The forces are balanced, so you've got gravity equal to the radiation pressure. That's why it's nice and balanced. But then the hydrogen is going to start running out, and it's going to become a supergiant. It's going to get bigger. It's going to start fusing helium because hydrogen runs out. Forces now are not balanced because gravity is less than radiation pressure. So the radiation pressure is massive compared to gravity. This is why it gets bigger. And then once the helium runs out, it's going to explode. So heavy elements that were fused in the core are scattered into space. It's a huge explosion. And then it's going to contract in on itself. So fusion of gases is totally stopped now. Forces are not balanced. Gravity is way more than radiation pressure, especially in a black hole. So it'll either become a black hole or a neutron star, depending. I mean, this fella is only 22 times bigger. Is likely to become a neutron star. Describe formation of a solar system, clouds of gas and dust. This is your top answer on the formation of anything in space. Collapse under gravity, gravitational attraction. Question 4 then. This is quite a tough one because we get into question 4 now and they start increasing in difficulty. But bearing that in mind, they will throw some easy questions at you. So just don't get to question 4 and think, oh, I'll ignore this. Have a look. So here's one. Look, state Newton's third law. So object A applies a force to object B, and object B exerts equal and opposite force back on A. Okay, that's Newton's third law. You need to know his laws because that's an easy 2 marks. Explain how this third law applies to the rocket. Well, if we have a look, you've got the rocket pushing on the water and the water pushing back on the rockets, and that's pretty much what I've written there. Now, this question for 5 marks is a tough one because it gives you a distance and it gives you some energy. But it wants to know, so what it's saying is, at this height, at 1 meter, it's got 5 joules of potential energy. So let's work out how much kinetic energy it's got. That's what the question entails, really. How much kinetic energy has it got at 22 meters per second? So I've written everything I know there because I've also got the mass and the gravitational field strength from up by here. And then I've gone for kinetic energy equals half mv squared, which I've got from here. So Ke equals half mv squared, which I think is the first equation we're using on question 4 in this paper. So that's going to be 0.5 times the mass, 0.5 times the velocity, which is 22. It's going to give me 121 joules of kinetic energy. But it needs to be the total energy now. So potential energy, which is 5 joules there, plus your kinetic energy, which is this, is going to give me 126 joules. Now I can find out the height that it will reach. So it's essentially adding this 1 meter on to whatever I'm going to get now. So I've got 126 joules. I need to use now, remember, all these energies are interchangeable. So potential energy, kinetic energy is all energy. Now I need my mass, my gravity, and my height to get my height. And that formula is this one. So it's PE equals mgh. So my h is I need to get. So I put it in a triangle. I've pushed my PE up to the top, which gives me these 3 together. I put my finger over h. H equals PE over mg. And your mass is 0.5, your gravity is 10, your total energy is 126, and you come out with 25.2 meters is the maximum height it could reach. But we'll go to this question. I think I need to keep this out. Let's shrink that. Explain why the rocket will not actually reach this height. Well, not all that energy is transferred. So some is lost as sound as heat. It makes a noise when it's going up. So it's pretty much the work done against air resistance is going to lose energy. Okay, not all that kinetic energy is transferred. The initial acceleration is 4 meters per second. Use Newton's second law. Well, Newton's second law is F equals ma. So again, we need to know those laws. So I've got my mass of 0.5. It hasn't changed. I've got an acceleration of 4. what's this resultant force? 2 newtons. So that means that it's accelerating by 2 newtons. That's the resultant force when you take one away from the other. And we'll show you that now in the next question. Calculate the size of the initial thrust force. Now, to do this, we need to know what the weight of the rocket is. And when we have a look at this diagram, it hasn't given us a weight, but we can work weight out using W equals mg. And we know mg, because mass is 0.5, the gravitational field strength is 10. So the weight is just going to be 0.5 times 10. It's going to be 5 newtons. There we are. I haven't even written that. Look. Now, if it's 5 newtons going down, I've drawn a little diagram here. So when forces are balanced, they've got 5 newtons going down as weight and 5 newtons as that reaction force. But it's got a 2 newtons of resultant force. So that means now I need to plus my 5 plus 2 is going to give me my initial thrust force of 7. So my 7, I've got, so if this is 5, this is going to be 7, this arrow. Difficult question that, so don't be concerned if you're thinking, oh my god. A student suggests that the resultant force increases as the rocket gains height. Give a reason why. Well, the rocket mass is going to decrease because its weight is decreasing as water is ejected. So this arrow is so the weight is gradually getting smaller and smaller. That's why the resultant forces are going to increase. And we're on 11 minutes. Let's see if we can do this. So a lot of information again. Be careful because they're giving you 2 technetiums, 99 and 99M. I've made a mistake before where I've used this as my half-life, but this is the actual half-life we need down here because it's on about 99M. But state the number of protons. Well, it's got an atomic number of 43, element 43. So that means there's 43 protons. The decay that wasn't mentioned, so gamma and beta had mentioned, alpha decay wasn't mentioned. That's 2 protons, 2 neutrons. It's a helium nucleus. Then we come on to the Timothy table, which is a big one in this case because I've got to get to 60 hours because 2.5 days equals 60 hours. So I've done my number of half-lives there, which is going to be 10. My time, so each half-life, 6, 12, 18, 24, and I keep going up until I get to 60 hours because that's how long it wants. And let's see how far it decays. So 5 times 10 to the power 4 is just 5 with 4 zeros at the end. So it's 50,000. And then it keeps halving, half, until I get to 48.83, which is, you know, you could round that up to 49 becquerels there. Isotope technetium with the longest half-life. So this question is basically asking you, how can this support... Yeah, this is a really tough question with 2 marks. I'm going to need to read the question here. It has a half-life of 4.2 million years, and in 1952, technetium-98 was detected in a red giant star, which is billions of years old. Explain how the discovery of technetium-98, these stars add support to the theory that heavy elements produced in the stars. Well, anything that was initially there would have decayed because our decay rate is 4.2 million years. Well, these stars are billions of years old. So any technetium-98 initially present in the star would have all decayed, so it must have been made later in that star, towards the end, when it was dying. And that is that paper, I think. Yes.